Hi, good day to all. In this particular presentation, I'll be discussing geometrical mean radius or GMR and geometrical mean distance. Myself, Dr. Ismail C., retired professor, Government College of Engineering, Kannur. This is a topic from Kerala Technological University Power Systems. So we will moving to the presentation. What is GMR? The definition or the expansion of GMR is geometrical mean radius. It is again called a self-GMD or self-geometrical distance. This is usually denoted by the symbol ds. This GMR is used for the calculation of inductance in power transmission lines. We have already know that the formula for the inductance is L is equal to 0.5 to logarithm of d by r into 10 raised to minus 7. Now I am expanding this and I'll be getting inductance is equal to 0.5 into 10 raised to minus 7 plus this 2 into 10 raised to minus 7 logarithm of d by r. So in this equation, L has two parts. The first part is, or the first term is 0.5 into 10 raised to minus 7. And the second part is 2 into 10 raised to minus 7 ln d by r. Actually, the first part represents the inductance of the transmission line. It is due to the magnetic flux present inside the conductor. So, by using the concept of GMR, our aim is to eliminate this term or eliminate this term from the expression. So, our expression will be such a way that 2 into 10 raised to minus 7 ln into, instead of this d, we will be using geometrical mean distance, and instead of this r, we will be using geometrical mean radius. Okay, further moving to the concepts. We will see how GMR removes that particular term 0.5 into 10 raised to minus 7, or it is mainly due to the internal flux linkage inside the conductor. For that purpose, we are replacing our solid conductor by an equivalent hollow cylinder with a very thin surface. So in such a hollow conductor, if an alternating current flows through that particular conductor, the flux inside the conductor will become 0. And we all know that it is due to skin effect. Since it is a hollow conductor, there is no internal flux inside the conductor. Since there is no internal flux inside the conductor, there is no interaction between the flux and the current. Therefore, we can simply eliminate the term 0.5 into 10 raised to minus 7 from the earlier equation. We can see the concept through some diagrams. The first diagram shows that a solid conductor. If such a solid conductor is using for transmission of power, when current flows through that, we know that the magnetic flux lines are there inside the conductor as well as the outside the conductor. But if we are using a hollow conductor instead of that, the currents will be confined to the hollow conductor surface. Now you again think that hollow conductor with a very thin surface, then we can fully eliminate the inside flux. We can fully eliminate the inside flux. That means if you are replacing the solid conductor by a thin hollow conductor, the AC flow flux inside the conductor will be fully zero. That in this manner, we can eliminate the term 0.5 into 10 raised to minus 7 from the inductance equation. So in this particular condition, we have to note these points. Always the hollow conductor radius is always less than the solid conductor. And that hollow conductor is chosen in such a way that we have to compensate for the internal flux. This diagram depicts that the solid conductor is having a higher radius than the equivalent hollow conductor. And we can easily derive that this geometrical mean radius is equal to, usually represented by R dash, is equal to 0.7788 into R, where R is the physical radius of the conductor. Now we will see what are the dependence of GMR on conductor parameters. Before that, what is the advantage we are getting by eliminating this term? That is, we already have an equation with the two terms. By incorporating the concept of GMR, we will get the equation, inductance equation is equal to 2, simply it is equal to 2 into 10 raised to minus 7 ln d by ds, where d is called the self GMD or GM, and ds is called the GMR. Sorry, this is wrongly written here. This is the distance, and it is correctly written. This is ds. ds is equal to 0.7788 into r dash. The corrections from my side, I will correct it again. That is, L is equal to 2 into 10 raised to minus 7 L d by ds, where d is the distance between the conductors and ds is the radius. ds is the radius of self GMD, or it's again called GMR. From this expression, we can see that the GMR of a conductor depends on its shape and size, and it does not depend on the spacing between different line conductors. Now, we'll be moving what is meant by geometrical mean distance. As I mentioned earlier, GMD is also called a mutual GMD and GMR is called self GMD. This mutual GMD or GMD is used in the calculation of mutual inductance of the transmission line and it is denoted by the symbol DM. What is GMD? It simplifies the calculation of mutual inductance of bundled conductors. What is its definition? Definition is geometrical mean distance between one conductor and another. It is the geometrical mean distance. It is something similar to GMR. It is called GMD because it presents the mean distance between conductors. Since GMD is the distance between different conductors, varies with conductor arrangement. That is, in the earlier case, GMR does not depend on the distance between the conductors, but GMD depends or varies with the conductor arrangement. Now we will see how this varies or how to find out the GMD, geometrical mean distance, under different cases. First case, I'll be considering a single phase line where two adjacent conductors I am considering. In usual case, as depicted in this diagram, A represents the single conductor and B represents its return path. The important term here is what is the distance between these two conductors. So in this special case, the mutual GMD or simply GMD is the distance between the centers of the conductors. That is, in this case, only we have to consider one distance. That is the distance from one conductor to the other conductor or conductor A to conductor B. That's all. That is why here it is simply the distance between center of the conductors. So we'll see another, we'll moving to the next case. Here, I'll be considering a three-phase transmission line. Here, the mutual GMD is equal to the equivalent equilateral spacing between the conductor, or it is the geometric mean of the distance between the conductors. So, there are two cases. One is symmetrical three-phase line and another one is unsymmetrical three-phase line. And here also there will be two more classification that will come later. Symmetrical means the phase R, Y and B are connected or placed at the corners of a equilateral triangle. But in unsymmetrical case, the distance between R and Y will not be equal to Y and B and will not be equal to B and R. That is D12, D31, D23, they are unequal. But in symmetrical case, these distances are same. That's the difference between symmetrical and unsymmetrical arrangement. So we will see what are the GMD or the equilateral spacing, equal and equilateral spacing between in both cases. In the first case, in both cases, GMD is the cube root of the product of distances between the conductors. How the cube roots coming? So here there will be three conductors. So we have three distances. So the GMD is the geometrical mean distance. What is meant by geometrical mean distance? That is the cube root of each of these three distances. So if you take the first case, symmetrical, in this case, G12 is equal to G23 is equal to G31 is equal to, let it be D. So GMD is equal to cubic root of D into D into D. It is nothing but D. So in a symmetrical case, the GMD is equal to distance between any one of the lines. Now, for the unsymmetrical spacing, the unsymmetrical spacing, GMD is equal to, or D equivalent is equal to cubic root of D12, D23 and D31. As I mentioned, there will be two configuration three-phase line, usually either an horizontal configuration or a triangular configuration. We already defined what is mutual GMD with respect to a triangular configuration. The same formula applicable to horizontal configuration also. The only what matters is the distance between each of those lines. In this case also, there will be the distances are distinct differences are there. They are different. That is R to Y, D12, Y to B, D23, and B to R, D31. So they are different. So the formula for mutual GMD is equal to, usually represented as ds, cubic root of D12, D23, and D31. And that distance is also known as equilateral spacing between unsymmetrically transposed line. Now, to understand it correctly, we will solve some numerical problems. The first problem, it is related to a single phase line. It's given as two-wire transmission line, which is 15 kilometer long, is made up of round conductors, each of 0.8 centimeter in diameter, separated from each other by 40 centimeter. What is the GMD of the configuration? What are the given data? The diameter of the rounded conductor is given, that is equal to 0.8 centimeter. What is the distance between them? That is a separation between conductor D is equal to 40 centimeter. That is also given in the problem. To confuse us, another data is also given, 50 kilometer long. With that is the length of the transmission line. In this particular case, that data is not needed. Actually, that is not needed for the GMD calculation. Then radius of the conductor, we all know that it is diameter divided by 2. So I am getting 0.4 centimeter. Then what is the geometrical mean distance? We already mentioned it, or already know that in a single phase case, the geometrical mean distance is nothing but the distance between the lines. What's the distance between the lines? 0.4. So here the answer is GMD is equal to 40 centimeter or 0.4 meter. Very simple. Now coming to the next problem, problem number 2. It is a single circuit three-phase line. Single circuit three-phase line. The frequency is also given here. Frequency is also given here. This three-phase line is arranged at the corners of a equilateral triangle configuration. The distance is also given, 5 meter. So what is the GMD? That is a question. So for a three-conductor triangle configuration, we already know that GMD is equal to cubic root of distance between each conductor. So this is the formula. So in this case, that distances are same. Hence, this calculation is not needed. But just for understanding the concept, we are just taking the distances and finding out the cubic roots. So final result is 5 meter. That is nothing but the distance between any one of the conductors. Why we are getting such an answer? Because it is a symmetrical configuration. It is a symmetrical configuration. So we'll moving to another numerical problem. With different distances between the lines or the unsymmetrical configuration. So the problem is 60 Hz transmission line a single circuit 3-phase 60 Hz transmission line consists of 3 conductors arranged in a triangular configuration. So again, not a horizontal configuration. And the distances are given between the transmission line. The first distance is 5 meter, second distance is 5 meter, and the third distance is 8 meter. So what is GMD? The formula is same. That is a cubic root of D12, D23, and D31. So what are the distances? They are given. D12 is equal to 5 meter, D23 is equal to 5 meter, D31 is equal to 8 meter. So just substitute in the formula. Cubic root of 5 into 5 into 8. All raised to 1 by 3. That is, I am, instead of using that cubic root symbol, I am using raised to 1 by 3. That's all. So by using calculator, if you are calculating it, you'll be getting approximately equal to 5.85 meter. So we'll be moving to a next problem. But the earlier problems are with the single conductors, that is not bundled conductors. Now the next problem is with respect to a bundled conductor. So we can read the problem. Calculate the GMD of a 3-phase circuit with the 2 conductor bundles. That is, in each phase consists of 2 conductors. That is, the bundle conductors are coming as a minimum 2 conductors per bundle, or 3 conductors, 4 conductors, etc. are there. But in this problem, we are using 2 conductors in a bundle. So for a single phase case, only 2, 1 phase and 1 neutral. Phase is using 1 bundle and the neutral is using another bundle. But since it is a 3-phase line, there will be 3 phases. R phase, which is using a bundled conductor. In that, there will be 2 conductors. R phase. In Y phase also, there will be two conductors, since it is again a bundled conductor. Actually, here there is a mistake from my side. Here it is B. It's not R, it is B. Sorry for that. So what are the distances between these conductors? That is from the center of the bundle, from the center of the bundle to the center of the bundle R to the center of the bundle by 5 meter. Then center of the bundle to center of the bundle B, that is again equal to 5 meter. What is the total distance between R and Y? Sorry, R and B, it is equal to 10 meter. So we will analyze this problem. So first, I'll be finding out the individual distance between subconductors. So first, I will be considering bundle R and bundle B, or A and B. I'll be either calling this as R or A, and this is calling either B or Y. Okay. So suppose that this is at 0. At this point, this is at 0. So the first conductor in the bundle R phase, is to the conductor Y. It is 5 meter. That is from center of R to center of first R to center of first Y. It is 5 meter. Similarly, the center of second R to center of second Y, that is again 5 meter. What about the distance between first R and second Y? That will be 5.3 meter. Similarly, the distance between second R and first Y, that is equal to 4.7 meter. So if you are considering the distance components between these 2 phases, that is R and Y, the equivalent mutual distances of this bundle to bundle, that is DAB, is the geometrical mean of these four distances. That is 1 by 4. 1 by 4th root of DAB is equal to 5 into 5.3 into 4.7 into 5. That is approximately equal to 4.99549. That is the equivalent mutual distance of one bundle to another bundle is, in this case for AB, I'm getting it as 4.99. So if you consider this Y and B, here also it is mistakenly marked it as R. It's not R, it is B. So Y and B is again the same calculation. So nothing to repeat. So it is a symmetrical configuration. So by symmetry, DBC is equal to DAB. So it's again 4.99. So what is the diff? What about the first A and C or R and B? That calculation will be different because the distance will be different. We will calculate AC, that is the first R and last B. What are the distances? First R and first B is 10 meter. Then first R and the second B is 10.3. Then second R and the first B 9.7. Second R and the second B is again 10 meter. So what are the distances? 10, 10.3, 9.7, 10. Here also we have to find out the equivalent distance for bundle to bundle distance. It is 10 into 10.3 into 9.7 into 10 into all raised to 1 by 4. This is approximately equal to 9.9. So how to calculate the GMD now? That is, we already calculated bundle to bundle mean distances. Bundle to bundle mean distances already calculated. Now you use the formula for the GMD. It is a cubic root of DAB, DBC, and DCA. So just substitute the values we got from the earlier slides. So you're getting 6.29535 meter. Our final answer is 6.295. Now you can think of whether this much accuracy is needed or not. That is, usually the distance, the diameter or the radius of the conductor will be very, very small compared to the distance between the transmission lines. So is it necessary to do this much accurate calculation, or we can simply neglect that radius? We will see. That is we can consider, nothing is mentioned about the arrangement of the conductors in the problem. So we can consider like this also. That is the bundle can be considered as this also. So in that case, in this, I am assuming that the radius is very much smaller than the diameter. Sorry, very much smaller than the distance between the each conductor. That is here 5 meter, but the radius is 30 by 15 centimeter only. That is comparatively less. And here I am not taking that value. So what is my GMD? GM is the cubic root of DAB into DAB. Sorry, here again another mistake made from slide. DAB into DBC into DCA. Okay. So GMD is equal to cubic root of 5 into 5 into 10. It's equal to 6.3 meter. What is the answer we got earlier? It is 6.295. A small point not 5 meter difference is there. So almost we are getting the same answer. So you can, from this what we understand, what we can do is we can simply neglect that while considering the distance between the transmission line, we can neglect adding radius or subtracting radius with the distance between the transmission line. Simply take that distance only, then we'll be getting almost the same answer. Thank you. Thank you for watching.